The next speaker is now Raymond, and he will talk about terrestrial planets here and abroad, basically. Okay, Sean, please.
All right, well, it's a pleasure to be here to tell you guys about our review chapter on terrestrial planet formation at home and abroad. And just to get us started, here's an image of 4 terrestrial planets, 2 of which are at home in the solar system and 2 of which are in an extrasolar system. And just in case any of you don't recognize, this one's Venus, that one's Earth, and these 2 are extrasolar planets. They're obviously, artists' impressions. They're from the Kepler-20 system. And even among the co-authors, 2 of the 5 of us work in our native country. Eiichiro Kokubo and Kevin Walsh both live and work in their native country, and the rest of us are abroad. So we kind of sample these at-home and abroad things. And before I get going, I should mention the other co-authors, Alessandro Morbidelli and Ryuji Morishima. And Sean Raymond is me, just in case you did not know. All right, so here we go. Terrestrial planets. In the solar system, it's very easy to tell apart the terrestrial planets. They're the little rocky planets closer to the sun. But when we talk about terrestrial planets in the general sense, it's not as obvious as we would like. This plot shows the measured bulk density as a function of mass for the known planets where there are such measurements now. Extrasolar planets, that is. And you can see that there's a whole diversity in terms of the densities of these objects. And so, for example, these lines here are kind of fits to the general trends, but there's a lot of scatter on top of that. So what if I was to say, well, I think anything with a bulk density of 3 or larger probably has a solid surface, so let's call those terrestrial planets. Well then, anything, I would say terrestrial planets have to be less massive than, say, 5 or 10 Earth masses. But even among that range, there's some planets down here that have very low densities. Are those things really terrestrial planets or not? I don't know. This is a slide of a question to kind of ask ourselves. I don't really have the answer here. But it's neat that we're actually able to address those kind of questions now rather than just speculate about them. So on to the topic at hand of terrestrial planet formation. So let me give you some context of where this is all happening. So all the action is taking place in a circumstellar disk of gas and dust around a young star. We start off with small grains. Those somehow become planetesimals. And Anders Johansson told us about this earlier today, about how that kind of process can happen. So in my talk, we're assuming we already have things that are planetesimal sized. The next step is that planetesimals coalesce into larger objects we call planetary embryos. These are things, think, objects the size of the moon or to Mars. That is, say, 1% to 10% of the Earth's mass or so. Then, while there's still gas in the disk, those planetary embryos can migrate. They can launch density waves in the disk, and those density waves can torque the planet's orbit and move it around. They can move the embryo's orbit inward or outward, although usually for things that are, say, Earth mass or smaller, the migration would be inward. While you have gas in the disk, a large enough planetary embryo can act as a giant planet core and grow into a gaseous planet. And gaseous planets can also migrate. They can do what's called type II migration, so they can basically carve annular gaps in the gas disk. At that point, the evolution of the planet is basically linked to the radial motion of the gas. And we think that what these gas disks are doing is basically slowly falling onto their stars. That means that they're dragging these planets inward with them. Once the gas is gone, systems of giant planets can also become unstable. So what this little cartoon here is trying to show is 2 giant planets starting off on nice concentric circular orbits. For some reason or another, they become unstable, their orbits start to cross. Then they have, basically one of the planets is ejected, and what remains is an eccentric orbit. So that kind of thing can happen. And also, once the gas is gone, we have kind of the final assembly of any remnant planetary embryos and planetesimals into terrestrial planets. So there's a lot of things going on, and lots of these things influence the terrestrial planets that we're going to talk about. And so I'm not going to be able to cover everything in here completely, but I'll touch on a lot of different aspects of this during the talk. So let's get started. First, I'm going to cover just briefly 2 different ways of forming planetary embryos. And so remember, These are kind of planetary embryo-sized things, the Moon and Mars. The kind of typical, the classical picture of planetary embryo formation is that they form kind of from a sea of planetesimals. And they form by two distinct processes. Early on, you can have runaway growth. If one planetesimal gets a little bit bigger than its neighbors, it can gravitationally focus other planetesimals onto it, and it can undergo a really rapid phase of growth called runaway accretion. But then, once that planetesimal gets so big that its gravity stirs up the random velocities of nearby planetesimals, that basically shuts off the gravitational focusing, and you enter into this different mode called oligarchic growth. And oligarchic growth is named that way because it's kind of oligarchic ruling is the ruling by the few. So oligarchic growth is the growth by the few. So in the simulations of this process, you typically end up with, say, tens of planetary embryos around, the inner solar system, and they have characteristic masses and characteristic spacings. They're typically, say Mars mass-ish or a little smaller, and they tend to be spaced by, 5-10 Hill radii or so. Another process to form planetary embryos was recently shown by Michiel Lambrechts and Anders Johansson. And what's going on there is you can form planetary embryos directly from pebbles as long as you have a seed of an object that's, say, at least as big as Ceres, which is maybe 10 to the minus 4 Earth masses or so. So what you're seeing in this image are the streamlines, the flow lines of particles that are either coupled very strongly to the gas or not. So the solid lines are strongly coupled to the gas, and the kind of the gray lines are objects in the same initial paths, but that are not strongly coupled to the gas. And you can see the objects that are weakly coupled to the gas, they're just deflected by this core, this growing planetary embryo. But objects that are strongly enough coupled to the gas, once they enter inside this critical radius, the Bondi radius, their orbits are basically so strongly perturbed that they can be very efficiently accreted by the growing planetary embryo. And they can have a super runaway phase of growth. That phase doesn't last that long, but during that phase, you can still grow things very quickly and very large. And so then that phase of growth transitions to more like an oligarchic regime as the Bondi radius grows. Now, on to the late stages of accretion. This is kind of the final phase of terrestrial planet formation, where you have a whole bunch of planetary embryos and planetesimals in a planetary system, and you're bashing them together. So there's a lot of exciting stuff going on. Lots of things that can make artists draw pretty pictures. And so let's take a look at what's going on here. So you're going to see several movies like this. So let me walk you through this one. So what this movie is showing is the eccentricity on the y-axis versus semi-major axis of a whole bunch of small bodies that are going to grow and coalesce and dynamically interact. The color of each body corresponds to its water content. And so I've kind of painted the initial distribution of bodies here by some initial water content, assuming that everything close to the star is dry, and as you go further out, you have some water. And so when you see an object change color during a simulation, that means that there's a mixture from bodies from different zones. So that's an indication of basically radial mixing within the disk. And this matters because we think this might be the source of water on Earth. So here we go. There's also a Jupiter mass giant planet out here at 5.5 AU, and we'll see its influence shortly. So boom. So you can see objects kind of stir each other up just by self-scattering in the inner disk. In the outer disk, they're stirred up mainly by resonances with Jupiter, and then self-scattering by objects that were excited that way. This guy here is going to become our kind of an Earth analog. And so you can see it's still red there. It's still dry. But you can see there's some blue things that are approaching 1 AU, and then boom, now it changed color. What did that mean? That means that water-rich material ended up being, through multiple scattering events, ended up at 1 AU, bashed into the Earth as it was growing, and delivered water. And so you can see this is a very chaotic phase. There's lots of close encounters and scattering events and collisions. And the final sweep up of these small bodies takes, 100, 200 million years. So in this particular simulation, we end up with planets that look something like Earth and Venus, another planet that really does not look at all like Mars, and I'll come back to that, and some remnant stuff that's kind of like an asteroid belt. So what happened here? What actually happened? So during this simulation, you can kind of track the bodies that were accreted by each planet. And the feeding zones of the planets actually change in time. It's kind of neat. So as a function of time, what you're seeing here are the impacts that occurred on each of those final planets. So if you look just at the blue ones, those are the impacts that occurred onto the planet that ended up at 1 AU. So you can see early on, it was accreting things mainly that started at about 1 AU. So this is the starting orbital distance. But after, a few million years, its feeding zone moved outward and kind of spread out, and it was able to effectively accrete things that started off throughout the disk. You can also kind of sort of see this by eye, but the biggest impacts happen pretty late, so you have enough time to grow big enough impactors. So if you look at the growth of the planets, so let's look again at the kind of the Earth analog here, the middle one. You can see it kind of grows slowly in time. It bashes into another embryo, but then it has these periods where it's growing kind of diagonally. That means it's growing from lots of small bodies, and then every so often there's boom, big impacts with other big ones. So these kind of big impacts are the kind of impacts that we think form the moon, for example. We think that the last giant impact on Earth was the moon forming impact. Okay. So just to kind of summarize a few key factors that determine the outcome of late-stage accretion, I think you can boil it down to just two real factors that are key to doing this. The first one is just how much stuff you have. And so that's basically the disk properties, the disk mass, how much mass you have in planetary embryos and planetesimals, and where that mass is, the density profile of that material. That's kind of the key factor number one. Key factor number two is the degree of eccentricity excitation within that material. And so why this one? Well, imagine you have a population of planetary embryos. If the typical eccentricity of this guy right here is relatively small, so over the course of an orbit, its radial excursion goes about this far, well, then I guess it can bash into these guys, but it can't bash into those other guys. So you're going to form something that looks maybe something like that. All right. But if its eccentricity is bigger, then it can bash into all these guys, and you'll form something bigger. And an even more extreme case, for which I did not make arrows, you can imagine if its eccentricity was really big, and it crossed that whole disk of embryos, then you could turn them all into one big planet. Okay? So that's why the eccentricity excitation matters. So now let's apply these models of late-stage accretion, where we think we have some idea of how they work, to some real systems. So we'll start off with the abroad. We'll do it backwards. Instead of home and then abroad, we'll do abroad, then home. So we're going to talk about extrasolar planetary systems. So to start off, let's talk about extrasolar planets that might really be, terrestrial. And what am I talking about? I'm talking about the systems of hot super-Earths. These have been detected in the last 5-10 years, and they're just recently known to be very, very common. Something like a third to a half of all sun-like stars has a planet less than, I think it's 10 or 20 Earth masses within about a half an AU. So that's a lot of planets like this. And they tend to be found in multiple systems. They tend to be found in pretty compact orbits, but not typically in obvious resonant chains anyway. And so I grabbed some of the Kepler data just to make a plot of this. So here are 9 planetary systems, just to kind of get a feel for the kind of things they look like. The x-axis here is in log. And the reason is, some of you may notice that one of these planetary systems looks very familiar. It's this bottom one. This is actually the terrestrial planets of the solar system, where there's semi-major axes all divided by 10. And so, Mercury, Venus, Earth, Mars. And I did this a log scale because then the dynamical spacing of the systems is the same. The period ratio is just represented by a distance between objects. And so you can see the Venus-Earth dynamical spacing, period ratio, is pretty characteristic of these other systems. They're compact because they're crammed into a smaller physical space, but dynamically speaking, they're similar to our own terrestrial planets. Okay. I think I had a slide showing you the tag numbers if you're interested. And so how do these things form? There's 2 models that I think still work. Many models have been proposed to explain the origin of close-in super-Earths, and 2 models still hold up. So I'll go through each of them. The first is in situ accretion. So the same kind of story I've been telling you already, but very close in from very massive disks. So what do you need to do this? You need a close and very massive disk, like I just said. And so Chang and Laughlin have a recent paper on this where they showed that they did something really neat. They basically constructed an analogy to the minimum mass solar nebula. They constructed a minimum mass extrasolar nebula. And so these dots here are the basically spread out masses of hot super Earths. They took these observations from Kepler. They assumed a mass-radius relation. They spread out the masses of each planet, and they kind of fit a disk profile to it. And this red line here, or alternately the histogram, is what they get out of it. So they get something that's basically has about the same slope as the minimum mass solar nebula, which is this blue line, which means the surface density that goes something like r to the minus 3 halves or so. But it's a bit higher. It's a factor of 10 or 50 higher. Is this realistic? I don't know. Disk people should answer that, I guess. But I think it's an interesting way to address the problem. If these planets really did form in situ from local, presumably rocky stuff, you can reproduce a lot of aspects of their orbital and mass properties. The trick is whether it's really in realistic initial conditions or not. And I don't know the answer to that. The other model is a migration model. So type 1 migration is that migration that I alluded to very briefly earlier, where an object of, say, an Earth mass or so, a planetary embryo, can launch spiral density waves in the disk, and the back reaction of those waves move the planet around. So here's a simulation, and the migration can be either inward or outward. For objects less than a few Earth masses, it's pretty much always inward. But above that, in some cases, you can have outward migration. So in this simulation, the initial conditions was a population of something like 50 planetary embryos from 2 to 15 AU, subject to type 1 migration from a, quote, realistic disk, a disk model that's not too bad. And so outward migration was permitted in some regimes in this disk. And so, for example, this red body that formed, you can see the mass growth on the bottom, this red guy that formed, it formed fast enough that before inward migration, before it migrated too far inward, it ended up in a little zone of outward migration, and it took off back outward. And so it just hung out by itself out at 15 or 20 AU out there. Everything else that did not grow fast enough to end up in the outward migration place ended up migrating inward and kind of growing into a system of hot super Earths by basically piling up at the inner edge of the disk. So everything migrated inward, but the disk doesn't go quite onto the surface of the star. It stops at some distance, at least in this simulation. And so these embryos basically migrated inward and piled up at the inner edge of the disk. And the kind of system that you get from this type of simulation looks qualitatively like some of the hot super Earth systems. So for example, here's Kepler 11, and here is this particular simulation. What's good about the simulation is you have a dense orbital configuration. What's less good is that you have a resonant chain. The inner planet's not actually in resonance because it was pushed inside the inner edge of the disk. But the other planets are in the resonant chain, which is not really what's observed. But you can imagine maybe this would serve to just increase the amount of solids in the inner disk and then transition to an in situ accretion type mode. I don't know. Anyhow, that is the other model for the formation of hot super Earths. And so that, where the real origin of those planets is still an open debate. Now let's talk about giant exoplanets. Those are not the focus of the talk, but giant planets play an important role in sculpting the terrestrial planets. And so we can learn something about the terrestrial planets that could form in these systems by understanding the dynamics of the giant planets. And so you've probably seen a graph like this before. We're looking at the orbital eccentricity versus semi-major axis of the known giant exoplanets as of, I guess it's slightly out of date now, but as of a couple years ago. And there's Jupiter is somewhere out here. It's at about 5 AU, an eccentricity of about 0.05. There are a few good Jupiter analogs known, but only a few. Much more common are planets with either high eccentricities or that are very close to their stars. And so we think that there's kind of two key dynamical processes that have shaped this type of diagram. The first being type 2 migration, that inward migration of giant planets after they carve a gap in the disk. and the other being planet-planet scattering, where you form planets in multiple systems on relatively circular orbits. Those orbits go unstable, and maybe one planet's ejected from the system. And the planet or planets that remain tend to have eccentric orbits. And these eccentric orbits are basically the scars of violent instabilities in their past. So we're seeing this, and we think that this happened. Okay. So let's see what effect these two processes have on terrestrial planet formation. So to start off, let me show you another simulation like the one before. But in this case, we have a giant planet that's going to migrate through this disk of stuff. And there's also gas forces are felt by these small bodies by an assumed simple disk. Okay. So this planet's migrating inward. These vertical lines are the 3-to-2 and 2-to-1 mean motion resonance with the giant planet. Those resonances basically act like shovels and push a lot of this material inward to the giant planet's orbit as it migrates. But some objects get a little bit too close to the giant planet, and they get gravitationally scattered outward onto eccentric orbits that really should be unstable, but the giant planet migrates out of the way, and so they're stranded like that in weird orbits. And so you can see, shovel this way and scattering that way. So this is just for the migration phase. If we want to see what happens on longer timescales, we can look at this movie here. And so this is the same type of setup, except there's a little extra outer disk of stuff. So the movie's going to run for much longer, so you'll see the migration phases a little faster. Boom, see, it's over. It's already done. You see the migration produced two close-in terrestrial planets by that shepherding mechanism. It scattered a bunch of stuff outward. The orbits of the outward stuff were slowly damped by the disk, but then the disk was dissipated after 10 million years. Things entered a chaotic phase similar to what we saw before. And the final sweep up of material out here takes longer than the simulation ran. It would take billions of years to finish. But at the end of this simulation, we formed kind of two interesting planets. There's this close-in giant planet. It formed this, even closer in hot super-Earth type planet. And this was one of the mechanisms proposed to form hot super-Earths before their statistics were well known. And this mechanism was basically ruled out because I don't think there's any systems known, actually, where you have a close-in giant planet and a hot super just interior to a strong resonance. But the migration also produced some terrestrial planets kind of in its wake, behind its orbit. And so this guy here is an interesting case. He's about 3 Earth masses at, about 0.9 AU. And what's interesting about this guy is he's very blue. Why is it so blue? It's because during the migration, the eccentricities of all these things got really large. And so the feeding zones of the planets became really wide because they could accrete objects from across the outer planetary system. And so this guy is dark blue because it has a lot of water, because it was able to incorporate a lot of material that accreted far away from the star. Presumably volatile rich stuff. So this is the kind of planet that could be, covered in oceans, which is cool. All right. So here's another slightly less happy situation. So imagine the solar system was just a little bit different. Instead of Jupiter and Saturn, we had Jupiter and 2 sub-Jupiter things. And everything else was basically the same. You have an outer disk of planetesimals that actually doesn't matter too much in this case. And you have an inner disk of planetary embryos and planetesimals. So don't pay too much attention to this. This is the dust flux that was produced by the planetesimals, but it's not too relevant for our situation. So let's just see what happens here. So we got these nice 3 planets. They're bouncing around. The inner disk is doing the same thing as we've seen before. Planetary embryos are scattering off each other. They're growing. By this point, they're more than half the size of the Earth, the largest ones. And everything's going fine. So I think this will just produce something that looks like the solar system. Oh, but wait, the movie's slowing down. Something's going to happen. And boom. All right. So that is a dynamical instability. So the giant planet's orbits went unstable and destroyed everything. Everything, all that terrestrial material was dumped onto the star. All the planetesimals get ejected. We basically took something that looked like the solar system and transformed it into something that looks like an extrasolar planetary system. And in the process, destroyed all the cool terrestrial stuff. Okay, so now we're going to switch gears back to the at-home part. So we have some kind of understanding of late-stage accretion, of the effects of different processes, and we want to try to really understand how the inner solar system forms. And there's lots of constraints. We know a lot about the solar system, not as much as we'd like, but a lot. So any model of the inner solar system has to reproduce at least this list of things. The masses and orbits of the terrestrial planets. In particular, they're very circular orbits. They're not perfect circles, but they're very low eccentricity of the terrestrial planets. The structure of the asteroid belt. That's not the primary goal of this kind of model, but you can't screw up the asteroid belt either. Right? You also have to reproduce the accretion timescales for bodies for which that we know the accretion timescale. For the Earth, we think it took at least the timescale for the last giant impact on Earth is about 50 million years or so, maybe a little longer. But for Mars, it's very short. It's only a few million years. So that we have to be able to reproduce that. And hopefully, we can get some water on the Earth. This is kind of like I mentioned here, this is kind of the weakest constraint, because there are other models for how you get water on Earth. And so it's a little model dependent. There's some debates and such. But basically, I would argue that the building blocks of the Earth were probably pretty dry. And you probably need some kind of delivery of those blue bodies onto the growing Earth to deliver water. And that's what I'm talking about. So classical models, kind of most simulations that have been done to date, make a simple assumption, which is not a bad one. They assume that the gas giant planets, which had to form during the gas disk lifetime, which we know is pretty short, we assume they formed first, and they basically shaped terrestrial planet formation afterwards. And that's what I call kind of the classical model. All right, so basically kind of a two-step process. These guys formed first, and then they shaped these guys. The trick is, what were Jupiter and Saturn's orbits at early times? We don't know what they were. There are reasons to think that they weren't the same as they are now. There's this model called the Nice model that you'll hear about in, I think, Melvin Davies' talk, in which an instability in the outer giant planets at late times caused the late heavy bombardment. So before the Nice model, we had to kind of rewind the giant planets' orbits to what they might have been beforehand. And there's good reason to think that Jupiter and Saturn may have been on more compact orbits, maybe in 3-2 resonance, and probably with lower eccentricities than they have now. You know, eccentricities, instead of about 0.05, of maybe 0.01, 0.02, something like that. That's kind of one story that holds together. Another story that holds together is that Jupiter and Saturn were basically on their current orbits, but they had slightly higher eccentricities. Why higher eccentricities? Because during the accretion process, I don't know if you realized during the movie I showed you before, a lot of that material that started off in the asteroid belt didn't survive. It got ejected. It had close encounters with Jupiter, and it got ejected entirely. And by ejecting those planetary embryos, that actually has an angular momentum transfer with Jupiter and Saturn, and it tends to decrease their eccentricities. So if we rewind to before that phase, we have to have their eccentricities be slightly larger than they are today. So that first movie I showed you was basically from the first assumption, assuming Jupiter's orbit at early times was nice and circular. Here is a movie showing the other assumption. What if Jupiter and Saturn had their current orbital distances, but slightly higher orbital eccentricities? And so, same setup as before, except there's also Saturn out here that also affects Jupiter's orbit. You'll see Jupiter kind of bouncing up and down a little bit. And you'll notice right away, there's a very strong secular resonance at about 2.1 AU. So, here we go. Oh, one other thing is that you'll see little error bars here and there that correspond to the sign of the inclination of objects that are on quite inclined orbits. Okay, here we go. So you saw pretty quick, this new 6 resonance, it's called the new 6. It's a secular resonance with Saturn. It's a very strong thing. And so anytime anything gets into that resonance, what happens is its eccentricity is driven up and up and up, and it hits the star. And that happens within a couple million years. And so that resonance basically chops the interplanetary system in two. And so the outer, this part doesn't really see the other part. And it also acts to efficiently remove material from kind of the Mars zone. So as these embryos grow, they're scattering each other around. If one gets scattered a little too far, it's gone. It hits the sun. Right? And so it's kind of, it's a nice way to clear material out of there. Okay. And so what you see in this particular simulation is this blue guy is going to end up being a pretty good Mars analog. It's going to have a long wrestling match with this other guy, and in the end, the other guy is going to get chucked into the sun, which is really the proper outcome of any wrestling match, I guess. And so there you go. You got two, Earth and Venus analogs and a pretty good Mars analog. So to recap, we have these two kind of assumptions for what Jupiter and Saturn's orbits were at early times in this classical model. And here's what they do. In terms of mass and orbital distance, here in gray are the planets that formed, and in black are the actual terrestrial planets. So this is with Jupiter and Saturn on low eccentricity orbits and more eccentric orbits. And the biggest problem here is that Mars analogs are terrible. They're way too big. It's what we call the Mars problem. Mars has historically been a huge pain in the ass for these kind of simulations because it was very, very hard to get right. On the other hand, these ones do get pretty good Marses. They're maybe a factor of 2 too big, but they're pretty close. But there's other problems. Earth forms dry. Like I mentioned, that's not as big a problem because it's a weaker constraint. But it doesn't fit with what we think the giant planets were doing before, the evolution of giant planets within gaseous disks. It doesn't fit with the later history of the solar system. It really is the kind of thing where it's not that satisfying because it screws up all sorts of other stuff. So we don't like it too much. So we want to see if we can make this model work better. All right. So how can we do that? Well, maybe our initial conditions are wrong. And instead of having a disk of embryos like this, we had a disk of embryos like that, a tiny little ring of embryos. And that seems kind of silly, but if that was the initial condition, here's what you get. Brad Hansen showed this really nicely a few years ago. Here's, again, mass versus distance. The solid dots are the actual terrestrial planets, and the open circles are simulations. And you really reproduce the terrestrial planets ridiculously well with this really goofy assumption. And it's very strange. So in this case, Earth and Venus are big because they formed within this annulus of embryos, or planetesimals and embryos, and Mars and Mercury are small because they were scattered beyond the edges. And so their growth was cut off at early times, and they didn't grow very big because of that. And one way you can make an edge at 1 AU is by plopping Jupiter at 1.5 AU. All right, this seems like a totally crazy thing. So let me explain why it might not be so crazy. So let's think about what Jupiter might have been doing during its formation, but not too hard because I only have a couple minutes. So here's what we think probably happened. Jupiter probably formed as a core somewhere. It accreted some gas, it became a gas giant, and it started type II migrating. That's basically what we think Jupiter did. All right, what about Saturn? Well, we think Saturn was doing the same thing, but maybe a little further out, and maybe a little later because it was a little further out. So, here Saturn's a core, it's growing, and then it starts migrating a little faster during this transition phase, and it actually catches up to Jupiter. It's natural that it catches up to Jupiter. And there's a really neat hydrodynamical effect that I'm not going to talk about now that turns around migration in that case. And Jupiter and Saturn naturally migrate outward in that case. And they can go really far, but the disk doesn't last forever. So at some point, the disk goes away, and they stop on some orbits. Now, the Grand Tack model that I'll talk about in a sec assumes that this happened and that this turnaround point was at 1.5 AU, just the right spot to make that outer edge in the disk of embryos and planetesimals at 1 AU to form a small Mars. So let's see how that works. Here's a simulation of that. The green lines are the orbits of Jupiter and Saturn. Blue particles are simply particles that started exterior to the giant planet's orbits. Red ones started interior to the giant planet's orbits. The dashed lines are simply the asteroid belt. And what you see here is the planets migrate inward, and then they turn around and migrate back outward. And for our purposes, what's most important here is that this inner disk of stuff that's going to form the terrestrial planets went from being, something like 3 AU wide to very narrow. And how that happened was by the same mechanism we saw before. As Jupiter migrated inward, it shepherded some material interior to its orbit by resonances, then it turned around and moved outward. And the asteroid belt, even though it got crossed by the giant planets, it's not empty. It was actually refilled by both those blue and red bodies. The blue bodies end up preferentially in the outer belt and the red ones in the inner belt. And so to look at this in kind of eccentricity versus semi-major axis snapshots, Jupiter migrates inward, Saturn catches up, they go back outward and are stranded at some distance. Okay? And you naturally truncate the inner disk at 1 AU, which is what you need, and you refill the asteroid belt with a very low efficiency. But it turns out that the asteroid belt's almost empty anyway, so you kind of need to clear it out. And so this holds together pretty well. For terrestrial planet formation, what does this look like? So these are snapshots where the green things are embryos and the red things are planetesimals. And what you see here is Jupiter migrating inward, turning around and taking off. So basically shaping this annulus of embryos and then getting out of the way. And then after that point, the annulus evolves basically like in those simulations by Brad Hansen. But the initial conditions I showed you are not quite the right ones, because as Jupiter migrated back outward, it scattered some of those blue particles back inward. And some of those were planted in the asteroid belt, like I mentioned. We think they represent basically C-type asteroids. And for every one that was planted in the asteroid belt, 10 or 20 ended up on high eccentricity orbits that crossed the terrestrial planet forming zone. And so even though everything here should be dry, you have this tail of very eccentric objects that should have the same composition as C-type asteroids. And so the initial conditions basically for terrestrial planet formation should look more like this. Planetesimals and embryos that are formed in the inner disk, plus this kind of polluted area, pollution from these highly eccentric blue guys. And so let me show you what that looks like. Boom. Most of the accretion is over pretty quick, but as these embryos grow, those little blue dots just represent water-rich blue material that was accreted onto the terrestrial planets. And so in this case, Earth does indeed get water. It's not from the same mechanism as in those classical simulations I showed you before, where Earth's feeding zone kind of naturally extended smoothly out to a few AU. And there's this kind of nice mixing. Instead, Earth formed mostly from local stuff, but because of the dynamics of Jupiter and Saturn, there's this extra pollution component that naturally delivers stuff to the Earth. And that stuff has the same composition as what was planted into the asteroid belt, which is a very good chemical match to Earth's water. That's the story. So let me skip over this because I'm running out of time, and I'll just kind of summarize the key points that I hopefully conveyed. So first, embryos form from planetesimals or maybe from pebbles. 2 models. A hot super-Earth probably formed by either in situ accretion or type 1 migration, or maybe a combination of the two. Giant exoplanets really do big things to terrestrial planet formation. And the classical accretion models for the solar system have this really strong Mars problem, or self-consistency problem, if you like the other initial conditions. And the Grand Tack model naturally produces a small Mars, which is nice. And I'll stop there, and I've added something onto the terrestrial planets here that I hope that all terrestrial planets have. Okay, thank you very much.
Yeah, I think you're very close, or we are very close to the beer part, the beer session now today. But before that, we will have a few questions, of course, to Sean. Thank you very much.
Thanks.
We start in the middle here, Peter.
Peter Wojtke. My question is, when your blue particles come very close for a long time, shouldn't they lose the water? It's like a comet, basically, that should lose water. I don't know how long it takes, but maybe you can include a kind of time scale that would turn your blue dots into red dots?
Yeah, that's a good point. I mean, there should be some water loss during that process. It depends exactly what form the water is in, whether it's really an icy mantle or whether it's trapped in hydrated silicates. And so the details of that are something that people are looking into now. That's a good point. Yeah.
Hi, András from MIT. Thanks for the great talk.
Thanks.
It's fun. I'm also going into the same direction roughly. So if you have energetic collisions, then these collisions can also erode the water reservoir of the planet. And the other thing is that you simulate the formation process for 10 hundreds of millions of years. So you would also expect that you will have some photolysing UV radiation that also kind of depletes your water reservoir. Do you plan to go into this direction and simulate this?
So good point. So in terms of, in giant impacts, how much water do you lose? All right, this is a tough question. There's a couple people who have looked at this. There's a really cool paper by Genda and Abe in 2005, where they showed that as you bash embryos together to form terrestrial planets, the more water they have, the more water they lose, because the impact impedance of water is lower than rock. And so the way you actually lose the water is you have this shock wave that goes all the way around the planet in a big impact, then you fluff off the atmosphere, and then you lose water out the backside. And so that's one thing that's not taken into account here. That's a good point. If you just compare kind of those classical models with the new Grand Tack one, for example, the amount of water that you end up with on Earth varies quite a bit. So in the old simulations, we'd end up with something like 10 times or more times the water content that we have on Earth. And we just say, well, we probably lose 90% of it during accretion. And the models that I've seen probably suggest that you don't lose that much, like simulations by Robin Canup and Betty Pirazzo a few years ago suggested that you didn't lose quite that much probably. And so the new simulations where we only end up with a few times as much water on Earth might be better, but it's something that needs to be looked into more carefully. It's a tricky problem. So.
Okay, question up there, please. Yep.
Hey, Sean. Jonathan Fortney, UC Santa Cruz.
Hey.
Hey. Given that in the Kepler-11 system and similar systems, you often have 5 and 8 Earth mass planets that have appreciable hydrogen envelopes that are maybe 1 to 10% of their mass, so they're not really bare rocks. Does that force a much faster time scale because you have to accrete hydrogen in these sorts of systems? Is that a problem for the dynamical simulations that you showed, that they don't happen fast enough, or is that not really an issue?
I don't think it's an issue, but I don't know if it's been looked at carefully enough. So, yeah, I mean, basically, to do that, you need to be in the right place to accrete at least some, 1 or a few percent of your mass in a hydrogen envelope at the right time while there's still hydrogen in that place. And exactly what place you need to be in and exactly how big you need to be at the right time during your migration or in situ accretion is something that, as far as I know, hasn't been looked at too carefully. I know they addressed it a little bit in the Chang and Laughlin paper, and they thought that it was doable in some cases, that you would still have a remnant atmosphere. But that's all I know about that.
Okay, we continue here again on the left.
Sean, at the beginning you made the connection which is often made between, the same process forming the cores of the gas giants and the terrestrial planets. I'm wondering if we take what Anders said and just start with everything beyond 10 AU at, say, a few hundred kilometers per second, just to give you a kickstart. What's the main difference in that kind of Safronov picture and the, isolation mass and going to oligarchy at the outer solar system if you start with the bigger bodies faster?
So basically, why do you grow big cores in the outer part and embryos and small embryos in the inner part? That's a tricky question. So did I get that right? That was.
Well, I think not just that the difference in mass, but just what would be the fundamental difference of a classical picture if you jumpstart everything with 200-kilometer sized planetesimals in the outer disk?
How that would be different? I think the process would basically be similar. You'd still have the same general behavior. One thing I'm going on a slight tangent here because it just popped in my head, is that one thing that can really change things quite a bit is the size of the planetesimals. And so perhaps the size of the fragments, if you have a collisional evolution, for example. If you have small fragments, then you can really accelerate runaway growth and grow things large quickly. But apart from that, I think that the dynamics should be pretty similar in the two regimes.
Okay, in the back, please.
John Tobin, NRAO. I was wondering if you could say a bit about what Uranus and Neptune are doing during this time, and do they play a role in stopping the outward migration of Jupiter Saturn? Good
point. So in that little cartoon that I had of what Jupiter and Saturn might have been doing, Uranus and Neptune were in there, but I erased them so it would stay nice and simple. Basically, the outward migration of Jupiter and Saturn during that kind of last part of the Grand Tack can act to accelerate kind of the final phases of growth of Uranus and Neptune, but it can't really grow them from small bodies. So we think that they were already basically cores out there, things of at least a few Earth masses beyond Saturn's orbit when this was going on.
Chris?
Yeah, Chris Ormel, USA Berkeley. I like your movies very much. They're really great movies, really jealous.
Thanks.
My question is, how do you treat the gas in these simulations, and especially in the context of this Grand Tack model? I mean, things as eccentricity damping by torques.
So the stuff that's in there, it's a 1D disk that's calibrated to 2D, I think, hydro models. We include things like aerodynamic gas drag and type 1 damping with the Tanaka and Ward or Cresswell and Nelson kind of formulas, this kind of stuff. Is that what you're asking?
Is that just analytical expression?
Yeah, it's analytical. It's not a real hydro disk. It's a 1D disk where the disk profile, the gas velocity and density is taken from a 2D code, but it's not interacting directly with a real 2D code, just because of timescale issues. No.
Okay, we have 3 more questions. One up there, Christoph, first.
Christoph Mortazzini, MPIA. I was wondering if Jupiter comes so close in, it should accrete inside of the ice line. So it should accrete planetesimals of a certain composition. I was wondering if this is in agreement of what we know about the chemical composition of Jupiter, if you have ever looked at that.
That's a good comment. I have no idea. You're right. I mean, as Jupiter is plowing through this stuff, the accretion rate onto a planet itself as it migrates through is generally pretty low, but it should still get hit by some stuff. And so if you could detect that somehow within Jupiter, that would be cool. I really don't know how to address that one. That's a good point.
Okay, on the left.
Hi, Sean. Richard Parker from ETH Zurich. I think as well as the migration and planet-planet scattering, you can add the star formation environment in as like a mechanism to alter eccentricities and also the semi-major axis of giant planets. And especially if star formation happens in a substructured environment, you don't necessarily need a dense classical embedded cluster to form to disrupt planets and disks.
Oh, cool. So you mean just other stars that are close by adding extra perturbations onto the planets?
Yeah.
Ah, cool. That's a good point. Nice.
Okay, final question in the back, please.
Adam Frank, the University of Rochester. I'm just not sure if this was like Michael's question, but you sort of, in the beginning, only mentioned core accretion for the massive planets. If the massive planets formed earlier on via gravitational instability, would any of this change?
You mean in general, it wouldn't affect.
If a gravitationally active disk, does that really sort of change some of this?
It wouldn't have a big impact on it, no. It's the Grand Tack model, for example, has to happen kind of in the last phases of the disk evolution. And so if Jupiter and Saturn formed by gravitational instability much earlier, they would have shaped kind of those earlier phases a bit more. But if the Grand Tack happened, then the last phases should still have been the same. And so I don't think it would have a big impact anyway.
Thank you.
Okay, thank you, everyone. And let's thank all the speakers
All
of
right,
this
thank
session
you.
again. And so we can follow Sean's advice here, go to the beer session now, and otherwise I will see you tomorrow morning at 8:30 again. Thank you.